All right, let's go ahead, get started here. I look and feel awful, but the show must go on. So let's jump right into it before this medication starts to wear off. Now, in the last section, we were looking at the slope of the line tangent to the graph of some function y equals f of x at some point x equal a. And we said that that slope was equal to this limit. Oh, let's do this one. We said if that limit exists, then the slope of the line tangent to the graph of y equal f of x at x equal a is equal to this. And we denoted it like this, f prime a. We called it the derivative of f at x equal a. In this section, we look at the derivative as a function in its own right. And so we'll define the derivative function as this limit. This limit up here is a number. This limit down here is a function. It's the derivative function. We said that if this limit exists, then f is differentiable at x equal a. We say that f is differentiable on an interval if this limit exists at all points in that interval. F is differentiable on an interval. It's called AB. If f prime exists for all x in AB. Okay. So let's try and find one of these derivative functions for some function f. Show that f So I want to show that this function has a derivative, right? And that that derivative exists on its domain. So by definition, the derivative of that function is this limit. Okay. So let's take a look at this difference quotient and then see what happens to it as we let h get smaller and smaller and smaller, closer to 0. Okay, so, let me compute f of x plus h. That'd be 1 over x plus h squared. So then this difference quotient becomes 1 over x plus h squared minus 1 over x squared all over h. And if I dropped in h equals 0, I see I have the indeterminate 0 over 0. So I'm going to try and algebraically simplify this up so that I have an equivalent expression, but one that I can look at and figure out what the limit is. So I'm going to go ahead. I've got a complex fraction up here. I've got this big fraction that consists of a couple of little fractions. So I'm going to simplify it by getting rid of all these simple fractions. And I can do that if I multiply everything by the LCD, which would be x squared times x plus h squared. So if I multiply the numerator by x squared times x plus h squared, and the denominator by x squared times x plus h squared, I get this. Well, let's see, if I multiply that by x squared times x plus h squared, the x plus h squareds cancel, and I've got an x squared. Doing the same over here, I'd have a minus an x plus h squared. All over, down in the denominator, I've got h times x squared times x plus h squared. All right, well, I still have this 0 over 0. So let me keep going. Let me square this binomial. So I'm going to get that squared, and then 2 times their product. Okay, performing the subtraction in the numerator. The x squareds cancel, leaving me a minus h squared and a minus 2xh all over h x squared, x plus h squared. Oh boy, okay. I'm going to factor out the h and cancel it with the h in the denominator. And when I do that, I end up with this. See if I can sneak it in here. After I cancel a factor of h in the numerator with the factor of h in the denominator, it looks like I end up with a minus h minus 2x all over x squared times x plus h squared. And now this limit over here is no longer indeterminate. I can see what happens as h goes to 0. As h goes to 0, the numerator starts to look more and more like minus 2x. The denominator starts to look like x squared times an x plus 0 squared. So it looks like, let's bring this all the way over here. It looks like I end up with minus 2x all over x to the 4th. Or minus 2 over x cubed. Okay, let me erase some of this and put up what we've found here. We were asked to find the derivative of this function, so we fall back on the definition, doing all the work. We end up with this derivative is equal to a minus 2 over x cubed. Okay, well, what does that give me? Remember, our interpretation of the derivative hasn't changed. The value of the derivative at a point still gives me the slope of the graph at that point, which is the slope of the line tangent to the graph at that point. So in other words, if I looked at the graph of this function, 1 over x squared, it looks like this. Right? And now if I wanted to know, hey, what's the slope of the line tangent to the graph at, say, x equal 1, I'm trying to find the slope of that tangent line. Well, here I have a function that gives me the slope at any x. So f prime at 1 is minus 2 over 1 cubed, or negative 2. That's the slope of the line tangent to the graph of that function at that point. And notice here, let's just go do a minus 1. I like to see the picture up here because I see that, yeah, the slope of that tangent line is negative. Now, if I went over to the other side and said, well, what's the slope of the line tangent to this graph at minus 1? Well, here I see a positive slope tangent line. F prime at negative 1 is minus 2 over minus 1 cubed. Well, that gives me 2. So this function gives me the slope of the line tangent to the graph of this function at any point I want. Now, I should have mentioned that for these derivative functions, the domain of the derivative function are all the places in the domain of the original function where that limit that we just computed exists. The domain of this derivative is all real numbers except 0. It's different. This function is differentiable on its domain. All right, let me introduce some other notation here. So far we've been using this prime notation to denote the derivative. There's another way to denote it. Let's call this Leibniz notation. Leibniz notation. So if y equals f of x, then we denote the derivative in prime notation as y equal f prime x. Right? In Leibniz notation, we denote it like this: dy dx. Yeah, you might see somebody write it as df dx. I like the dy dx. You can think of this ddx as the operator that tells you, take the derivative of whatever this is with respect to x. So ddx of y, take the derivative of this with respect to x. Right? It's like this symbol tells me to add. It's the addition operator. This ddx is the differentiation operator. The value of the derivative at x equal a. In prime notation, we've seen it. It was this, f prime a. In Leibniz notation, I would denote that like this. It's dy dx, and then I draw this vertical line at x equal a. Okay. Let me just restate a theorem that we saw in the last section. But let me use Leibniz notation for this one. And I'll call it theorem again. We saw this. D dx of c equals 0, where c is a constant. Right. We saw that before in the last section. We said, yeah, graphically that makes sense. Because if I think of the derivative as giving me the slope at that point, then if I graph this constant function, I'll call my c right here, it looks like this. It's a horizontal line, and the slope everywhere is equal to 0. So d dx of some constant is equal to 0 for all x. And we also saw a version of this. D dx of x. That's equal to 1. Because we said this in the last term. D dx of any linear function. Remember, that was equal to m, the slope. So d dx of x, well, x is a linear function with slope 1, so it's equal to 1. All right. In these next few sections, we're going to see a bunch of shortcut rules which allow us to find the derivative function without having to go through that limit definition. And so here's the biggie. This is a big one. For all exponents n d dx, take the derivative with respect to x of x to the nth, it's equal to n times x to the n minus 1 power. Right. Leibniz notation, prime notation, we could write it, we could say something like this. If f of x equals x to the nth, then f prime of x equals n times x to the n minus 1 power. Okay, let's do an example like this, see some other rules, compute a few more derivatives, and then get on to the next video. All right, let's see here. Well, let's do the one that we just computed. We did this. We showed, using the limit definition, that if f of x is equal to 1 over x squared, then f prime of x was equal to minus 2 over x cubed. Right? We went through the limit definition and we discovered that. Well, now let's do it using that power rule. So, in order to use the power rule, I want to rewrite this as x to some power. All right? F of x equals 1 over x squared. Another way to write that is x to the minus 2 power. And so d dx of x to the negative 2 power, by the power rule for differentiation, it's negative 2 x to the negative 3 power, which is, of course, minus 2 over x cubed. Okay, a few more rules. These are called the linearity rules. Okay. So suppose that f and g are differentiable. Okay, so again, what that means is that these two functions, f and g, the derivative exists at every point in the domain of both of these functions. They're differentiable functions. Okay, suppose that f and g are differentiable, then this function, f plus g, is differentiable, and the derivative of that function is the sum of the derivatives. And the same is true for a difference when I take two differentiable functions and I subtract them. I create a new function, this function f minus g. This new function is differentiable, and the derivative of this function is the difference of the derivatives of f and g. When I multiply some function by a constant, I create a new function. This new function is differentiable, and the derivative of this new function is the constant times the derivative of f. Okay, let me use the theorems that we've seen so far. We have enough now to compute the derivative of every polynomial function. Let me just do an example of that, and then I'm going to pause it and get the next video ready. All right. Get rid of all this stuff here. And let me put up a third degree polynomial. Let's let f of x equal 2x cubed plus 4x minus 7. Let's find f prime. So linearity rules apply up here. I can think of this function as being the sum of 2x cubed and 4x, and then I subtract off 7. And I can compute the derivative then of this function by computing the derivative of this one, adding to it the derivative of that one, subtracting off the derivative of this one. So f prime x, well, let me get the derivative of this. So it's a constant times a function. So the derivative of a constant times a function is that constant times the derivative of the function. And by the power rule, this derivative would be 3x squared. Add to it the derivative of this function. Well, hey, I can think of this as a linear function with slope 4, so I'll just do that. Or I could think of it as a constant times a function and do the same thing that we did over here. And I'll subtract off the derivative of 7. Well, the derivative of any constant is 0. So here's my derivative function. What is this? 6x squared plus 4. Okay, let me pause and I'll come back with the next video.